Okay, now let's look about how we can use Mathematica to take a derivative of a function. Oftentimes this is fairly straightforward to do by hand, maybe much easier than doing an integral, but there are times for complicated functions with things like square roots in the denominator, something like that, where it can be a little bit complicated to correctly apply the product or chain rule and get the right derivative. So that's where Mathematica comes in as either a check for your work or a handy way to do a derivative quickly. So for this example, we'll do something, again, familiar from one of your previous assignments. We're going to take the derivative of an equation for a simple harmonic oscillator. So this would be an equation describing the position with respect to time. And in fact, let me change to make it more interesting. I will change this to x. Let me change that everywhere. Okay, there we go. Okay. So I haven't ran anything yet, so x is not defined. But we'll go ahead and run this first cell. So it's going to define a new function, and then it's going to just take the derivative of it. So here you can see this is the function that I defined. It's got the built-in functions cosine and sine. Omega and t and a and b are not defined. That's why they're still, even after I executed this cell, blue. And a simple syntax for taking just a first order derivative is just like you would write it down on your note paper, is just to use a prime. Okay, so here when I did the prime, you can see it correctly applied the derivative, pulling out the omega from the cosine and the sine. And then you can see here, it's a little bit subtle, but this term, when you take the derivative, you get negative sign. So you get it with a omega sine. And then this term here, when you take the derivative, you get cosine. So that term is now flipped here. Okay, if I wanted to take a second derivative of the same function, I can just use double prime. Again, similar notation to what you would do in a math class. Okay, so here I've taken the second derivative of my original x function here. Okay, and it's by default taking the derivative, if you can't tell, with respect to time, which is the only variable that this particular function depends on. If I wanted to do this to, for example, solve for the constants a and b, I'll just quickly show you how to do that. Okay, so in a previous video, I showed you how to use Mathematica to basically do some algebra for you and solve for a constant. That's what I'm doing here. So now I am evaluating the original function up here, this one, at t equals 0, and I'm saying that function is equal to 0. So this is me essentially applying a boundary condition if this was a simple harmonic oscillator and saying, okay, at t equals 0, the position is equal to 0. So let's see what happens when I evaluate that. The output says, hey, that implies, right, for that to be true, then I know that my constant a up here, which was previously undefined, has to be 0. Okay, so a goes to 0 within this particular restriction. If I wanted to find the other boundary condition b, I can specify that the first derivative of the function is equal to some value. This would be like saying for a simple harmonic oscillator that the velocity at t equals 0 is equal to some value. In this case, I'll just use 1. When that's the case, then I have this relationship that omega, that constant, has to be the same as 1 over b, or b is equal to 1 over omega. Okay, so that's just one way I can, again, use this to take the derivative of a function, and in this case, I'm just doing a little bit of extra math to show you how you can do something on Mathematica that you did by hand in lab last week. That's one notation for doing the derivative of a function. This does the exact same thing. It's just a different notation. So D is the syntax for the built-in function. The inputs here in square brackets, the first input is the function. The second input is the variable that I'm taking the derivative with respect to. So in this case, t. And so I'm actually going to evaluate this one separately. Let's see here. I'll go ahead and evaluate this. Okay, again, just what we had before. That's just the first derivative of my function x. And then when I evaluate the second one, the difference here, when I say t, and I put this in a list here, I want to take the derivative of t and then comma 2. This says, hey, I want to take the second derivative, and I can increase this. This is the third derivative. I want to go up to the sixth derivative. I could do that as well. So it's just continuously taking the derivative of this function. But this right here, it's not saying t is 6. It's saying what is the order of the derivative you want to take. Okay, so first, second. Okay, and again, just like anything else, if I want to take a derivative and then maybe use that function later, I can define a function that's equal to the derivative of the function. So here I'll say, hey, we'll make this more meaningful, v of t, the derivative of x. Okay, and now I can, if I want to say, hey, what is v at a particular time? And it'll plug in 10 for t. Okay, notice here, actually, this is worth talking about. Even though I used solve to tell me what a and b are equal to up here, it didn't make a equal to that. It just says, hey, this implies that a is 0. It did not set a equal to 0 within the notebook. Okay, I'd have to either set that manually or use some other notation to do that. Okay, next I'm going to show you how to take the derivative of a function with respect to one variable at a time. You might have a function that depends on x, y, theta, r, and maybe you only want to take the derivative with respect to one of those variables. So syntax is similar. Here at this top line, I'm just going to clear f and x so that I'm starting from scratch, and then I'm just going to display what this function looks like that I'm going to take the derivative of. So this is straight out of the Mathematica help. It's just a function sine x times y over x squared plus y squared. So this is a function that depends on both x and y. In this line of code, I'm going to take the first derivative of the function. That's what this built-in function defaults to when I don't say anything other than x over here. So this says, hey, take the first derivative of this expression with respect to x only. Okay, so let's go ahead and evaluate that. If you look carefully at what this is relative to this, you can see that what happened was we took the derivative of that function with respect to x only. And again, this one being doable by hand, but a little bit tricky. And again, I've saved that function as f. And so now if I wanted to use this and maybe put in values for x and y, I could, or if I could use it to plot or something like that, it's stored. Now what I'm going to do is I'm actually going to, I'll call this f2 here. Okay, I'll take the derivative of this function, which I just saved, and now I'm going to take the derivative of that with respect to y. Okay, so I'm going to take the derivative of this function that I just saved as f here, and I'm going to take the derivative with respect to y instead of x and y only. Okay, so here you can see output is a fairly long expression. All right, so just to prove to you, like there's a little bit of shorter-hand way to do that. If I want to just do what I just did in a single step, so take the derivative first with respect to x only, so a partial derivative with respect to x, and then a partial derivative with respect to y, I can use this built-in function to do both. So here's the original expression, and then what this is saying is take the derivative with respect to x only, then take the derivative with respect to y. So let's go ahead and evaluate that. You can see that it is the same as the function above, which I did in multiple steps.